let me start by thanking the organizers for inviting me for a warm introduction.
You did invite the right person.
So it's my special honor to give the very last talk of this conference, the seminar series, and I mean, it was a very nice time here, and it's friends and family, so it's a nice environment to give a talk. So, right. So some of the people complained about the title that yet another approach doesn't sound too enthusiastic. There are two settings where this already works, and if you're happy with them, I don't want to convince you to use another one. So let me briefly start by presenting the other settings that already work. So you might decide that this is good for you. Whatever. Yeah. So, if you're a rational person, and most of us here are not, but if you are, then you probably are not that interested in that what's coming. So, because everything works over rationals anyway. So, there's a nice model. So, if you have a space, then you can sort of find a completely algebraic description of it. You can associate the Sullivan cochains, APL of X, which is a cochain complex, and I will grade this dually because I'm a topologist, I like differential going downwards. So for me, this is a chain complex. It's a chain complex of rationals, and this has very nice properties. So this is amazingly a commutative differential graded algebra on rationals. So strictly commutative, that's the key thing. And so it's a model of the singular chain complex. So let me do notice about this. So if you're interested in rational cohomology, this is your chain model. And it's a commutative differential graded model that actually relates to the cup product that we usually use. So it's not something exotic as what you think it is. And I mean, this can be used to completely describe homotopy types of rational spaces. So there's this correspondence. So if you have two finite type spaces, say nilpotent, then this can be completely characterized by this structure in the following sense. So you have two rational spaces, and they are weakly equivalent if and only if APL X is weakly equivalent as a commutative differential graded algebra to APL of Y. And this is important. You have to remember the algebra structure. So how does this actually go? I mean, so this is due to Alfred Guggenheim building on what? Of Coulomb and Sullivan. So what you do is you take your space X, you take the Sullivan cochains, APL of X, and then you build a minimum model, and then you can actually make this more precise and ask one isomorphism of the minimum models. So rational homotopy theory, this is it. So you can reduce rational homotopy theory for reasonable spaces to commutative differential graded algebras. That's one approach. So, what else? Well, if you over FP, you know that this can never ever happen. I mean, many people prove, and I will give references later, that this is an infinity algebra. So it's a differential graded algebra, which is homotopy commutative. If you take the cup product on cochains, that's homotopy commutative, and not only that, it's commutative up to all higher homotopies you can think of. But this can't be strictly commutative, because, for instance, the T-naught operations only live because it's not commutative. I mean, the first instance is the cup-1 product, and this is the homotopy that says that this is homotopy commutative. And its non-triviality gives you the first Steven Sagave. So it can't be. So there's an obstruction there. Well, what is the way out? You can still do things, but they're just vastly more complicated. So you can still characterize homotopy type. So let K be a commutative ring. And whenever I write K in this talk, it is a generic, not fixed commutative ring, but otherwise I don't care what it is. Then, I mean, this is a geometric thing coming from restricting faces, so it's a geometric thing, it doesn't care about the ground ring. As long as this is commutative, you will always get an infinity structure on the cochains. So, and I should drop some names, but the list is not complete. Mandell certainly, Press, and then there, everyone has his or her favorite infinity algebra, infinity operator. So, I mean, there are tons of different ways of showing this. There's not a canonical infinity operator, so there are choices involved, but it doesn't really matter. And then there's an important theorem of Mandell saying so if you have x and y finite type, now integral finite type, and nilpotent, then x is weakly equivalent to y if and only if the corresponding cochain algebra is W, which is are weakly equivalent. But now you need to choose a covariant infinity operator, and they have to be equivalent as infinity algebras. So this is the, it should flash, right? Because this is pretty annoying. I mean, even finding an infinity structure is bad enough, but then constructing a map. I mean, this means you have a zigzag, so I mean, it might not be that easy if you don't know this. Producing a weak equivalence of infinity algebras is pretty hard. So you have to control the full structure, and then you can reduce this. So, but of course, if you like to work with infinity algebras, that's perfectly fine. You can reduce the question of homotopy type completely to the question of the cochains. You just have to control the homotopy type of the cochains, but and in their natural habitat, so as infinity algebras. Right, what is the drawback of this? If you think about the constructions you like to do, they're way easier if you know that something is commutative. So think about bar constructions, multiplicative structures on bar construction. Think of Forschritt homology. So everything is easier if you have something strictly commutative. So this E infinity thing is hard to control. I mean, not completely, there are bar constructions, there are other constructions, but they tend to be quite involved. So, but okay. So if you're a rational person, or if you're a fan of infinity algebras, then you can stop listening and play Sudoku or whatever you like to do.
Well, what is cochains, by the way? What are cochains?
Well, so this is really take this space means simplicial set. So take your just simplicial set, map it to the integers, and do the obvious thing with the alternating cophase maps. You can go normalize. This doesn't matter.
Which infinity algebras are realized?
You can take Barrett-Eccles, you can take the subjection operator, I don't know. So
I mean, which infinity algebras do you get as cochains?
it is
Space, yeah.
it is that model, just a normalized cochains, for instance. Just a naive thing. It has a natural.
Yeah, but if you have
What's
some
the essential limit?
abstract infinity algebra, when is it C star of a space?
Well, there's a recognition theorem also here. I mean, as in rational homotopy theory, you can construct a backwards functor that takes an infinity algebra to some simplicial set, and then there's some criterion when this is actually sort of actually coming from something genuine. So when
Over Z it's not always true.
well, the problem is, I mean, even in the rational case, you get a global equivalent equivalence, but then the correspondence is only for finite type nilpotent, so you have a restricted thing. Yeah, not everything is allowed. You can't have a wild homotopy type. So what we want to do is, we want to replace this by something commutative. Well, and then you should say, but you just told us that over P this is impossible. So, of course, I can't just take the cochains. So I have to do something. So why is this possible? So with Brookshinsky, we proved the theorem that if you have a cofinite infinity operator and you take the algebras over that, over some arbitrary but fixed commutative boundary, then the good news is that there's a chain of equivalent equivalences so you take the thing that we want to understand, this is where the cochains live, right? This is what we want to have. And then you can actually go to two wells where you can realize this is something commutative. You can either go to commutative algebra spectra over the magnetic length spectrum. So if you're happy with stable homotopy theory, this is definitely the way to go, and then you will take the function spectrum of X. But if I add algebraic here, then there's a different side of the story where you end up at something like this. So these are commutative cochains. So we know that somewhere out there, there's a commutative algebraic model that wants to be discovered. So the question is, this is a zigzag. I mean, this is not
How long?
2. This is just 2. but still, math's going the wrong way. So, I mean, you can pull this through, but then it's ugly and large. So we want something here that is a model for the commutative cochains, and we know that it has to hit this with the correct infinity algebra structure. So not just any model, but the correct one. So the plan is now.
What is cochains?
I explained.
Oh,
So the plan is. So what is this? And then secondly, actually produce model. And it's an explicit model, and for those of you who know rational homotopy theory, it's actually very close to the Sullivan cochains. It looks similar. It's just a jazzed up version. So I could pretend that everybody was in Christian's talk, but I don't. So let's recall what the setting is. So the I up there is the category of finite sets and injections that already pulled up in Marcel-Bechter's definition of HHH. It pulls up as Fi in the representation stability world, and so this is something you have seen in some way or another, even if you don't know. So what is I? It's a category whose objects are just natural numbers with 0, and I just denote them by an underline to distinguish them from natural numbers floating around. So the only thing I might have to explain, so this is the set from 1 to n, and the convention is that there is the empty set. And morphisms are just injective functions. From n. So not order-preserving permutations are allowed, and they're really needed. Right. So what are some observations about this? Well, the empty set is initial. So this is initial. Then you have, this is a category, it's an EI category, so every endomorphism is an isomorphism, and you have that. You actually get the symmetric group on n letters at the SD automorphisms. And what you also have is that I is commutative. So it's a symmetric monoidal structure where the associativity and unit condition is strict. And this is just because you know how to glue sets together. So you just define n, some n to be the set with n plus m elements. Then the empty set is the strict unit. It's visibly associative, and you have a shuffle map that does this, and this is the twist map, and that's all there is. So this is a very nice category, and it gives you the symmetric groups with a little bit of extra flesh around. So, definition, an I-chain complex X is nothing but a function from the category I to chain complexes over K, and this is still my fixed but arbitrary commutative ring. And these are unbounded chain complexes. I want that chains and cochains can live in the same world. So These are chain complexes and the differential is down. So this is a functor category, so you can take these things as objects and natural transformations as your morphisms. So how should you think about this? How does an object look like it? Well, you have a sequence of things. So you have a chain complex at 0, at 1, at 2, and at 3. And then you have structure maps. So you can work with this like you would for simplicial, in this case, co-simplicial things. So 0 is initial. You have two maps like this. So you have two maps here. And here you already see that the symmetric group comes in because you can take that one, and this is the symmetricalized image of the other one. So, and then the fun starts. I mean, up to now this looks innocent, but at this stage you can count, and that should be 6. So, so what happens here? You have the order-preserving maps. But then you can also twist them. So these are the 6 possibilities. So if this helps, you can think of this as being a semi-co-simplicial object, which is co-augmented and which has some symmetric group action on the objects. So that's not too far off. So this is a co-augmentation map because, I mean, things are shifted. This has one element, so this is like the 0 in the simplex category, so this would be a co-augmentation. And then you only have the co-phase maps. But then, I mean, here you have the symmetric group action, and this is actually the important part of the structure. This is how these things look like. And then you can push your abstract nonsense button, and out comes a lot of structure for free. Well, you have a commutative category. Chain complexes have a tensor product. So you get a tensor product, which is given by a Dave convolution product. So there's a symmetric structure. If you have x and y, you lose the commutative structure that you have in I that comes from taking the disjoint union of sets. Here, you just take the pointwise tensor product. So you send an n and an m to x and tensor y m. So you end up in chain complexes. And then you model a Cohen extension, and you get a tensor product in the frontal category. That's the Dave convolution product. So it's just a Cohen extension. If you don't like this, this is extremely explicit in this case, so you don't have to know what this is. So if I want to know what x box times y is at level n, then I just take the colimit of the disjoint union of things mapping to n, and I take the external tensor. Be careful, this is taken in the category over n, where I'm only allowed to wiggle p and q inside the direct sum. I'm not allowed to cross things. But this is as explicit as it gets. So if you want to know a bit more about the structure, it helps to play around a bit. So what do we have? You take your favorite object, AI, and then you can evaluate M. Why not? So you take the I chain complex and you map it to the chain complex given by the nth spot. So this has a left adjoint. You can take the free diagram that starts on level M. There will be line. So this has a left adjoint. So you can build a free I diagram from a chain complex. So you take the chain complex and you map it to the function that frees things up to, this was exactly the wrong way round. This was C. So this is functorial in N, and it starts in M because if your N is smaller than M, you don't have any injections, so this starts in M and then goes up. And let's make an example. What happens if you do this? Well, you send N to the big direct sum over the maps from 0 to N. But this is initial, there's only one map. So this is C. So this is the constant function. So you have the chain complexes sitting inside of I chain complexes, just undisturbed as the constant object, like you can consider the constant simplicial thing or whatever. So, and this is extremely useful for many things, but this also means that you implement all the trouble you have with chain complexes into I-chain complexes. So what this also tells you is that you want to avoid the trouble that things can't be commutative. You must stay away from level 0, because there you just have the old trouble. So if I take the chain complex as 0, so this is just K if n is 0 and 0 otherwise, then I can consider this guy, and I don't want to write this. And then either you sit down and calculate this, or you use some abstract nonsense to see that this is the unit of the box time product. So this is the unit of this box time product. It doesn't contribute any information really, it just glues things together. Anything there. So, and now you have a symmetric monodal category. Well, it's associative. This also comes from abstract nonsense. This product is symmetric monodal. You have a twist map on your I category, you have a twist map on chain complexes. Gluing them together gets you a twist map on the box times product. So. And then you can talk about commutative monoids. Why not? So you get these are just commutative monoids in this I-chain complexes with the box time product. And I will often just say commutative I-chains. This is too long. a priori, it's not clear that this is a good idea at all, that this should have anything to do. But for instance, one thing that might make you optimistic is the fact that I as an initial object tells you that its classifying space is contractible. So you're not really causing any trouble, and actually I-chains with a suitable model structure are just equivalent to chain complexes. So in one way or another, you've created a lot of noise. But remember that we now have the symmetric groups acting as endomorphisms in this diagram category. And this is where things get interesting. So what is the relation, what is the interesting relation to chain complexes? I mean, you have the evaluation map, but that's a stupid idea, so you want a more interesting map to chain complexes. So the feature is there's a cochain type homotopy colimit that sort of associates from an I-chain complex and really glues the structure together to give you an ordinary chain complex. I mean, you always have this, I didn't say anything about model structures, but you have a homotopy colimit, but usually it's a huge and unmanageable thing. So the feature here is that this is extremely small and explicit. So I can actually define it for you. You do this, if you know about fit counting, this is just what you do. So first, so you start with an I-chain complex. And you just make it simplicial. So you associate a simplicial object to it. And some chain complexes. So you send your object in the simplicial category to the sum over the nerve of elements of length p. So and from here, so the flow with left and right. So yeah. So you have this. This is just implementing the nerve of the I category, which you know doesn't do any harm because the classifying space is contractible. And then you just take your I-chain complex and you evaluate it. So you're mixing all the evaluation maps that you have. And then the second step is something purely in terms of homological algebra. So if I want to take the homotopy colimit, I just take the bi-complex. X has a chain direction. Now you have a simplicial direction. So this looks like a bi-complex of that type if this is the p direction and this is the chain complex direction of x, and this will sit in here. So you get a bi-complex. Well, we want a chain complex, so we just take the total complex, and this is the sum total complex. I don't want it. So you don't take the product, you take the sum. And this is a decent model of the homotopy colimit. And it's very nice because it's small. You have a spectral sequence calculating its homology because it's total of a bicompact, so it's just nice. We didn't really invent this, so this was spelled out in work by Beatrice Gonzalez something, Rodriguez, yeah. But it was also in the year before. I mean, there was a diploma thesis in Bonn by Kimi on that. So I mean, yeah, it's not something, but it's a nice feature. So why is this good? If you start with a commutative mod on iTunes, and it's homotopy colimit is an infinity algebra, and it has an explicit structure of an infinity algebra over the Barrett-Eccles support. It's completely down to earth. You can write that down. And so this procedure actually gives you, it replaces one of the zigzags I had early on, the one in my work with Birgit Richter, by map. So so the homotopy colimit gives an equivalence of categories, shown the homotopy category of commutative ichains to the homotopy category of infinity algebras. So it's sort of, it's always nice if you can shortcut the zigzag. No, we don't have equivalence in actual explicit inverse yet. At the moment, we are happy with that statement. So, on the homotopy level, it's fine. But there should be an explicit inverse. And I also have an idea for it, but yeah. So,
what did you have an idea of something?
well, I didn't say that this is equivalence. No. So, but there is a promising functor backwards that wants to be an inverse.
That might be a
equivalent inverse. As this is recorded, I won't say more about this. Might be playing along. Sorry. So now we are sort of a tiny bit closer. So if we have a candidate, we only have to control this explicit homotopy colimit to show that we actually have the right thing. Actually, this is not what we do, but this could be what we want to do. Right. So maybe one word about the proof of one. So 2 is technical, there are construction and resolutions, blah, blah, you don't want this. But 1 is actually nice. You take the translation category of the symmetric group, so objects of the element in the symmetric group, and you just have a morphism by multiplication. And then this acts on I. This is actually going back to an idea of PMA. So what you do on objects, and it goes through, if you take a symmetric group element and you have n elements in your category, you just twist them and add them. So, and this is commutative, so this actually gives something reasonable. Otherwise, you might be in trouble with this being a functor, but it's actually fine. And then again, you push the abstract nonsense button. I mean, you have this action, then you get an action on the nerve, then you get an action, I mean, and the nerve is part of the homotopy colimit. So what this action comes about, you just add on the nerve here. So the nerve of the category sigma n has an action like this. And this is this. And then you just act on the indexing set. And the associated bicomplex functor and the total complex are symmetric, like symmetric nodal, so you can just write down an action. So this is, I mean, this is really a proof of one if you
true that if X has an action of the parallel operand in this category, then the homotopy problem will again get an action?
I mean, you proved something like this for spaces, right? It should go through, but I didn't think about it. But I would bet yes. Yeah. Right. So. What I want to build is really an I-chain model of the Sullivan cochain complex. So I should remind you what the classical thing is. So you first construct a simplicial gizmo, which in simplicial degree Q is the free polynomial algebra. There are some exterior bits, but I still write them as polynomial generators. So everybody does this in that area, so I mimic the bad notation. And then you say, this is a simplex, and then you're better imposing this condition because this is a simplicial commutative differential graded algebra. So you write down this nonsense equation and define the differential that way. So, and then you define, so if Q runs, this is sort of this, and then Sullivan defines the cochains as the map of simplicial sets. So you plug in your simplicial set and you plug in your simplicial commutative differential graded algebra. So the maps have to respect the simplicial structure. So the simplicial structure is gone. You eat it up by requiring this maps. These maps are compatible. So you're left with a commutative differential graded algebra of rationals. And that is the Sullivan model. This is not functor friendly because having relations like this is a nightmare. You don't want relations. You can never ever build a functor that way. So, but then there's a sort of reindexing trick that says, well, these are not really relations. They are augmentations. You can formulate this in terms of an augmentation. So we found this in at least one source of rational homotopy theory. So this is not due to us. So you just do this reindexing. So Si is Q0 up to Ti minus 1. And then you realize that actually APL is nothing but a two-sided block construction. Like this. So this is the free commutative ETA on the chain complex that has things in degree. I mean, we're still over Q. This is degree 0 and minus 1. Remember, chain complexes, cochains are negatively graded chains. So I take this. So this generator stands for the TIs. This one stands for the DTIs. And now they are shifted. So now these are the SIs and these are DSIs. This is a polynomial algebra like above. So you have Q adjoint S0, Q adjoint S1 up to SQ with the differentials. But then you act on this chain complex that just concentrated in degree 0, And this just indicates the zero augmentation. On a polynomial algebra, you have two augmentations. You can send the polynomial generator to 1 or to 0. So this is the S0 with 0 augmentation. And this is S0 with 1 augmentation. So the SI maps to 1 and the SI maps to 1. And then you take the bar differential on these SIs and they just implement this simplex condition and the corresponding differential condition for you via the augmentation. And this is functor friendly, so you just copy and paste and it works. So K is arbitrary commutative ring. And now the I version of APL in simplicity degree Q is just, well, I'll just let the bar construction running. So now I have a different unit, so that I take this, I take the free commutative gizmo, but now I free things up. So remember, this was the free functor from chains to I chains, but we know that we have to stay away from degree 0 because usually the free commutative thing on a disk is not a cyclic. And this is the main problem in homotopy theory because this makes everything break down. And usually you want a model structure such that the vibrations and weak equivalences are given by the underlying functor. But then the free thing of an acyclic generator for the cofibrations has to be cyclic, but it isn't. And this is really doing the trick. So you take your contractible chain complex, but you place it in positive I degree. And then, so this is just the free commutative I monoid on F1I of B0. So where now K is not Q again, it's just something. So this is B0. I take that chain complex with K, plug it in, and free things up. So the crucial thing is this is the target of an acyclic cofibration, of a generating acyclic cofibration. It stays acyclic. So there's stuff in degree 0, but otherwise it's just. So this acyclic means evaluated at every n. So this is the thing, and then you can just say APLI of X. You just mimic what Sullivan did. It's just a maps of simplicial sets from X into that I version of the Sullivan cochains. Right. And then the good news is that this works. So what does it mean that this works? So at the beginning I said we want a strictly commutative model of the cochains of an algebra as an infinity algebra. Then there was this lemma saying that the whole column is at least in the right world, and it's actually in the right world in the homotopy category. So, but this isn't enough. So let me just state this as one term, but it's so you look at this as a functor of spaces. And then Mike Mandell gives you a checklist, what you have to show, that then spits out for you that you have the right thing. So what he did is sort of write down a cochain version of the Einberg-Steamroller axioms. Because, I mean, how do we usually prove that the Einberg-Steamroller axioms hold? We write on chain homotopies, or we write on some things on chain level. So you can usually do this. And this is a cochain theory. In the sense of Mike Mandell. So you have to check things. This joint union goes to product and whatnot. So there are the analogs of these axioms that you have to check. But you can do this. It's actually, well, with the model structures, and so it's a few pages, but you can do that. So, and then Mandell tells you that there's a natural iso of infinity algebras between quasi-algebra between this homotopy colimit I didn't specify coefficients here, so for every commutative ring K, you can build this. It's an infinity algebra. You have to lift it up to make the infinity algebra coequivalent, and then you actually get a zigzag of quasi-isos in the world of infinity algebras between this one and that one. This, so it is what we aim for. Secondly, if you are a rational person, then we didn't do anything wrong. So, so for k equals q, there is a natural quasi-iso, and this is really a map. So now let me write down the coefficients. So this is now Sullivan's cochains, and you actually get a quasi-isomorphism. So rationally, this is the same, and this is in infinity algebras. Where here, this is a commutative differentiated algebra, so it has the trivial infinity structure, and it's an infinity map for that structure. This has a more complicated structure, but the map is one of infinity algebras. So in particular, all the cup product information and the higher information is preserved. So this is this, and what about spaces? I said we want spaces, right? So in rational homotopy theory, there's something really important as the spatial realization factor. So you take a commutative I-chain complex, and now you just use the other variants. So you say I assign a simplicial set to it by just forgetting the cochain structure of the Sullivan construction and just keeping the simplicial direction. So you define this as maps of commutative I-chain complexes. So this in the simplicial degree Q is just this. And then you can let this run, and this gives you a perfectly defined simplicial set. This sounds promising. This is actually part of a homotopy adjunction. So there's an adjunction on chain level. So simplicial sets say Z to DI is the same as commutative I-chain maps from P to APLI Z, and this passes to a homotopy adjunction. And then finally, if I work over the integers, I can take any ring, but then the finiteness condition has to be adjusted. So X as weakly equivalent to Y, if and only if. You just have to look at the I version. So this is weakly equivalent to the I version of the Sullivan cochains as commutative I-chain complexes. So you can control the homotopy type. I mean, this is now really the integers here, where I work over the integers. And so this is x, y, finite type nilpotent. If you want a different k, then this has to be k finite type. So you can adjust this if you want to any ring. And so you can characterize homotopy type just by working out the commutative I-chain structure of the Sullivan cochains. Thank you.
Questions?
So, can you, using this explicitly, model things like Steiner operations?
Well, the Steiner operations, yes, because you have the Barrett-Eccles action on the nerve of I, and other people have worked out what the cup-I products correspond to. So you can write down what a cup-I product is, just in terms of the Barrett-Eccles operator. So in the Barrett-Eccles operator, you have strings of permutations, and you take so it's a cup I, so you just take identity, twist, and you take that string, and that gives you the cup I product. Yeah, you can write that down explicitly.
Do you have
Okay.
minimal models in this
No.
context?
That's exactly, well, there are model structures around, and you can model cofibrin replacement. But not every cofibrin replacement has the features of a minimum model. And at the moment, we have not really a good idea what to pose as the correct condition, so that you can actually reduce this to saying that a minimum model of this has to be isomorphic to a minimum model of that. That would be gorgeous, but yeah, it's Christmas, so. Well,
So this question is designed to test how big this category is. Do you know the homotopy type of the space of maps between two free guys?
Oh,
So one of the features of the Mandell model is you know that homotopy type. You see the relationship between Dirichlet algorithms and Dural
no, that's a good one. No, I don't know. Yeah.
So this last part 4, is that an independent of Mandell's
No.
motive?
Well, I mean, 3 indicates that one can possibly prove that. But we are doing the lazy approach. As we compare this to Mandell's cochains anyway, we don't really have to prove it anymore. But, I mean, yeah, you can certainly do it via 3. But that's more model categories.
Could you spell out what your APL of Q is for a given index Q?
Yeah.
Is it possible to say?
So what do you get? I mean, this is a unit, so you don't see it. So you're just left with this thing here, and then you have the box times product Q times. Then this is number left adjoint. This is actually the co-product in the category of commutative I-chains. So this is isomorphic to F1I. P0 plus Q. Let's do this one. Do I get a tensor? No, that should be right. So yeah, so you just get a bunch of things. So, but I mean, the important thing is really this structure here. So the free commutative gizmo on that one. As, I mean, by definition, you just take the direct sum. Say, whatever. We've used up everything anyway, so. And this, I mean, the reason why this is contractible is really like, here you can pull this inside, and you get the free I thing on M, and then you have B0 and full tensor product with a symmetric group action. So, I mean, this is just free and deconvolution. Without this, this wouldn't be contractible. This is exactly the problem you have if you take a disk and the free thing, you have homotopy. But this spreads this out, and the sigma M action on this is free, and that's the thing. So you just get a bunch of tensor products of disks floating around. So it's just a Kunert formula that collapses all that to nothing.
So that's really why we want monomorphisms in order for that to be free. That's really where the monomorphism part is important.
If not, we should thank Birgit again.